Welcome back, everyone. We have here the worksheet for Chapter 22, which we're currently in the middle of covering in class. And that's going to be the last of the chapters for now on Exam 4. So as I recall, Exam 4 will be chapters 21, 22, and 26. But always double check the syllabus. The syllabus is always clear, exactly what's going to be on every exam. So chapter 22 is the first of two chapters, chapter 23 being another, related to reactions that take place on the carbon's alpha to a carbonyl. And we've already learned that we can halogenate in those positions, and we're going to learn over the rest of the week that we can also alkylate in those positions. And looking ahead, I see a nitrile in one of the problems. And nitriles, as we've already covered, are very similar in reactivity to carbonyl groups of the sort that you would find, let's say, in a ketone. So we've got a few reaction practice questions over here. In the first one, we have fairly complicated ketone, but in any case, there's one carbon on that ketone that is both alpha to the carbonyl, meaning next to the carbonyl carbon, and also bears at least one proton. And in class just yesterday, we covered the halogenation of such carbons. We said you can replace alpha hydrogens with halogens by treating them with the elemental halogen, and that can be either Cl2, Br2, or I2 in the presence of acetic acid solvent. And then, of course, also on your active homework, your online homework, rather than using acetic acid, they use an aqueous acid like HCl or HBr, and that will work also. The mechanism corresponds exactly. So be sure that you're familiar with the mechanism of this reaction. There is an example of a mechanism problem involving this reaction on the practice exam, for which you can also find the video also on this channel in last semester's playlist. So what happens during the course of the reaction is that we replace one of those alpha hydrogens with, in this case, a chlorine atom. And we know that it's only going to replace one of those hydrogens because it says one equivalent. Frankly, even if it didn't say one equivalent, as I've mentioned a few times in class, best practice is when you give a reagent like this, for that to mean one equivalent as opposed to an excess. So we will replace exactly one of those alpha hydrogens with whatever halogen we're given, which in this case is chlorine. So I would expect the major organic product to look like this. The next reaction is of a carboxylic acid. So remember, you need to recognize functional groups whichever direction they face, no matter which side of the molecule they're on. So if you only have memorized carboxylic acids facing towards the right, that's going to be a problem, because sometimes in the question, it will face towards the left. And so we're treating this carboxylic acid with bromine and phosphorus tribromide, which we will learn in class, results in two things. First of all, replacement of one of the alpha hydrogens of the carboxylic acid with a bromine, and it will also convert the carboxylic acid to an acid bromide. And so that's why you need a second step. You need an aqueous workup step to hydrolyze the acid bromide and bring it back to the carboxylic acid. So the resulting compound is going to have a bromine atom in the alpha position. Since this carbon is chiral, you will get a racemic mixture. Involving those two monobromides. And on the exam, if this question were on the exam, you would need to draw exactly one of those structures, not both, exactly one of them. But you do need to show stereochemistry at any and all chiral carbons. Like it says in the directions, you are responsible to show any applicable relative stereochemistry, but if the product is a racemic mixture, draw only one of the enantiomers. So I try to be very clear in my directions. And then finally, we are treating phenylacetonitrile with LDA and THF. Just a reminder what LDA is. LDA is lithium diisopropylamide. It's essentially, not essentially, it is the conjugate base of diisopropylamine. So there's diisopropylamine. LDA is the conjugate base. So it looks like that. That's an extremely strong base, and it's able to deprotonate alpha to either a carbonyl or a nitrile. And given a choice of locations to deprotonate, LDA will choose to deprotonate in the less hindered position. In this case, there's only one location it can deprotonate, which is alpha to the nitrile. So we'll deprotonate the nitrile. That will give an enolate-like compound with a minus charge next to the cyano group. And then we will treat that with 1-iodopropane, just so you see what this would look like, just to give you a clear visual aid. Reaction with LDA gives us that enolate-like structure. And after treating this with a primary alkyl halide, such as 1-iodopropane, this will now undergo an SN2 reaction, where the enolate carbon will attack the carbon bearing the leaving group and displace the leaving group. As a result, you will wind up attaching the propyl group, in this case, to the carbon that's alpha, to the nitrile, and all three of those carbons over here that I'm indicating in red come from the 1-iodopropane. So this is the correct answer. And I think you'll agree with me that we have the correct answer. Whoops, I just fell into my own trap. This answer, as I gave it here, would lose a few points because we've just generated a chiral center, so you need to show the stereochemistry. And either way is fine, wedge bond or dot bond. So I admit I just played myself. Whenever you generate a chiral carbon in a reaction and you're asked to draw the product, you need to show the stereochemistry. Oh, and I just realized I've got two wedge bonds over here. So I will fix that. It should be a wedge bond and a dot bond. This is correct. Let me now correct that, and then we'll re-upload that. There we go. we'll re-upload that and get rid of the mistake. So again, the way you know whether you need to show wedges and dots is if in a reaction question like this, the resulting product has a chiral carbon. Then you need to show either a wedge bond or a dot bond. Neither one of the two is any better or more correct than any of the other. They are equally correct. Wedge bond and dot bond are equally acceptable. Either way is fine. Because again, the question says if the product is a racemic mixture, draw only one of the enantiomers. So that's pretty much it for the reaction question. The question does not say to draw the mechanism, so you do not have to. But if you find that helpful to do so, then you may certainly feel free to do so. All right. Well, so much for the reaction questions. We also have some mechanism questions. I think a grand total of 2 of them. And these are both reactions that we will have talked about in chapter 22. So the first mechanism, let's move back to that. The first mechanism involves treating dimethylmalonate with sodium methoxide and methanol, followed by this dihalide, and the product results from attachment of that alkyl chain to that central carbon and loss of one of the halogens. The other halogen will remain. And by the way, if you wanted to, you could treat this compound with more sodium methoxide, and that will then connect this carbon that's attached to the bromine also to that central carbon. And you'll get a ring. It will look something like this. So these 2 reactions could have been in the same synthesis, potentially. So the point is, this is a malonic ester synthesis, and the reagents are very typical. Notice how the methyl ester matches the methanol solvent and the sodium methoxide base. That's very important. Everything needs to match when you're doing any kind of deprotonation reaction of an ester. That's something we'll hit pretty hard in class, probably on Friday as I speak. So we have the mechanism down here. And so the first step is going to be deprotonation of one of these 2 particularly acidic protons that sit right between the 2 carbonyls. And the reason those protons are especially acidic is because you get a particularly well-stabilized enolate ion, one that has at least 3 resonance forms. And so what I'm showing here is how to get to one of the resonance forms. But as always, when you have a resonance stabilized intermediate in a reaction mechanism, it does not matter which resonance form you show in your mechanism. It will always be possible to draw a correct mechanism using any of the resonance forms of the resonance stabilized intermediate. So we show methoxide ion, which is the base we're given, pulling off one of those central protons, moving the electrons in between the central carbon and the carbonyl carbon, at which point we must break the carbon-oxygen pi bond, otherwise that carbonyl carbon will have 5 bonds. And you get an intermediate that looks like this. Notice how I'm using the methoxide ion as a base. The way I know to do that is because I'm given sodium methoxide. Remember, CH3ONa is CH3O-. And as always, you'll notice I'm not even mentioning the sodium ion. The sodium ion plays no role in the mechanism. There is no way to write down alkali metal ions in a mechanism question and get any points whatsoever. It will never, ever do you any good to write down alkali metal cations in a mechanism. They are simply spectator species. They don't play any role. There's no arrows associated with them. You just leave them out. They're not even mentioned. Good. And so we get this enolate ion. As we'll point out in class, enolate ions are great nucleophiles, and they can react with an alkyl halide. This particular one happens to have 2 sp3 carbons with halogens on them. And of course, it doesn't matter which one the enolate attacks. Either one is fine. And you'll notice we're reforming the carbonyl in the diester. We're using the electrons in the carbon-carbon pi bond to form a new carbon-carbon bond. Those electrons will stay attached to that central carbon and form a new bond between that carbon and either of the carbons bearing the halogen. And then we break the carbon-halogen bond. Again, this is nothing more than an SN2 reaction, such as you learned about in chapter 11. And that gives us our product. So it's just those 2 steps. That's one of the reactions in the malonic ester synthesis that we will cover probably again on Friday. And then in the next mechanism, this one over here is the one that I will be saying in class will be on exam 4. And it's going to be a decarboxylation of either a beta diacid or a beta ketoacid, followed by tautomerization of the resulting enol to give the keto form. And all of that happens upon heating in aqueous acid. You will also get a molecule of CO2, which may or may not be mentioned in the problem, as it's an inorganic side product. And we're interested in the major organic product. So this is a reaction. I'm recording this video on a Tuesday. I'm expecting we'll cover it in class on Friday. And so I've even gone so far as to draw that first structure suggestively, just like we did it in class. And you can see that we have a 6-membered transition state here. All 6 of these atoms are lined up perfectly in the shape of a 6-membered ring. And so all we need to do is show the correct electron flow in the decarboxylation step. And that correct electron flow is with 3 electron pairs that move simultaneously. We'll see something really similar to this in chapter 14 in a reaction known as the Diels-Alder reaction. That will be another reaction that goes through a 6-membered transition state. And so the 3 arrows that you need to show are 1 going from the carbon-oxygen pi bond to between the oxygen and the hydrogen of the carboxylic acid. There will always be a pi bond like that, always, in this mechanism. The other arrow you need to show is breaking the OH bond of the carboxylic acid and moving those electrons in between the other carbonyl carbon and the oxygen. And again, there will always be bonds like that in a mechanism like this. And then finally, you need to show the electrons in the carbon-carbon bond between the central carbon atom and that carboxylic acid, carbonyl carbon. You need to show that flowing in between the central carbon and the other formerly carbonyl carbon. So all 3 of those arrows need to be there. They need to look just like this. There needs to be 1 forming a new OH bond. If you're not forming a new OH bond, it's wrong. And there needs to be 1 breaking the OH bond with the electrons going in between the oxygen and the carbon. And there needs to be another 1 breaking the carbon-carbon bond. From this, we will get a molecule of CO2. That's our inorganic side product. And you will get an enol out of this. And then we already covered in class yesterday how to go from an enol form to the keto form. And that's exactly what we'll do. Remember, the word keto doesn't mean the compound is necessarily a ketone. Any carbonyl compound with at least 1 alpha hydrogen will have a keto form and an enol form. And that's another thing we covered yesterday. And the way to do tautomerization from the enol form to the keto form in acid starts with one of the lone pairs. There will always be a lone pair on an OH oxygen. You need to move that inward to form a carbonyl group, and that's going to be the carbonyl of the keto form. And then you also need to show breaking the carbon-carbon pi bond and using those electrons to form a new CH bond. Those electrons will remain attached at the central carbon and form a bond to the hydrogen of a hydronium ion. And then, of course, you also need to break the hydrogen-oxygen bond. That will get rid of the plus charge and ensure that we have only one bond to hydrogen, which is what we need. So all of those happen in the same step. That will give you essentially the protonated product. And finally, all you need to do is use a water molecule, which again, we're given that. Remember, H3O plus implies that H2O is present, even if you're not specifically given H2O. If you're given H3O plus, then whether or not it mentions H2O, H2O is there. And that's going to be the most alkaline species in the solution because we're in an acidic medium. So we don't have any more alkaline species than water. So we show one of the lone pairs on the oxygen of water reaching out to grab this extra proton that breaks the OH bond. The electrons in that bond go into the oxygen and get rid of the plus charge. So that's a typical decarboxylation and tautomerization sequence. And that's all we have in this worksheet. There are other relevant problems in the practice exam. I believe I've given you a lot of resources to prepare for exam 4. So let me go. I will go immediately and upload the corrected worksheet so that this problem has the correct answer. And that'll be it. So have a great day, and I will look forward to seeing you all tomorrow and Friday.